Hi guys, it's Sam.
Hey guys, it's George.
And today we're going to be exploring simple harmonic motion to find the spring constant, K, through two methods. The first is the mass spring method, and the second is Hooke's law. And the materials we use are
Alright, so for the mass spring method, essentially what we did was first set up the apparatus, and then we placed a spring on the end of the rod. Afterwards, we placed a mass at the end of the spring, and then we pulled down. Thus, we can see the oscillations happening. This was recorded for 30 seconds. During these 30 seconds, the spark view was measuring the displacement of the mass spring system at a frequency of 10 Hz, and through looking at the data, we can determine the period of this spring.
Moreover, we found that amplitude does not affect the period. This is because a larger displacement results in a larger restoring force.
Alright, now on to calculations. As you can see here in the drawing, this is the mass spring system, and where t equals the period of one oscillation, which is the time for the mass to return to its original state. In other words, its position, velocity, and acceleration. M equals the mass of the bob, where the spring is assumed to be massless or negligible. K is the spring constant.
Rearranging the equation t equals 2 pi times the square root of m over k, we get k equals 4 pi squared m over t squared. Using the mass spring methodology, we found the average spring constant to be 33.8 newtons per meter.
For the Hooke's law method, we measured the displacement of the spring and mass at its equilibrium position.
The two forces acting on the mass are its weight and the spring, which have the force of mg and kx respectively, and they are equal to each other, so mg equals kx. Rearranging the equation, we get k equals mg over x, where m is the mass, g is the gravitational constant at Earth's surface, and x is the displacement of the spring at its equilibrium position.
Using Hooke's law methodology, we found the average spring constant to be 34.3 newtons per meter.
And now for epic statistics. The percent errors is calculated as the absolute value of the difference between the theoretical minus the actual divided by the actual value multiplied by 100. In this case, the theoretical value is the spring constant found through the mass spring method, and the actual value is the spring constant found through the Hooke's law method. We found the average percent error to be 1.46%.
To recap, we found the spring constant through two methods. First, the mass spring method, and second, Hooke's law. We found K to be approximately 35 newtons per meter, where the percent error was less than 2%, yet errors did occur throughout the experiment. Instead of going in the simple up and down motion, it also went in the right-left motion, skewing the results.